Okay, so windmills generate electricity by transferring energy from wind to a turbine. A study was conducted to examine the relationship between wind velocity in miles per hour and electricity production in amperes for one particular windmill. At that point, even teaching Algebra 1, teaching Algebra 2, students have a hard time distinguishing what's my X and what's my Y, what's independent, what's dependent, what's explanatory, what's response. Do y'all remember those words? Explanatory is your X variable, response is your Y variable. If you have computer output, it makes it really easy because whatever's by your slope, that is your X variable. Like there's no question about it, okay? So this is our Y-intercept, agree? Because it's either gonna say constant or intercept next to it. Whatever's below it, that's your slope. And whatever word is by your slope, that's your X variable. That's your explanatory variable, okay? For the windmill, measurements were taken on 25 randomly selected days. That's our sample size. Sample size is 25. What's weird about linear regression stuff when we're doing degrees of freedom? You have to subtract 2 from your sample size. So anything we do with degrees of freedom on this one is going to be 23 degrees of freedom. You get me? 25 sample size. So only for linear regression, we take the sample size minus 2 for the degrees of freedom. The computer output for the regression analysis for predicting electricity production based on wind velocity is given below. The regression model assumptions were checked and determined to be reasonable over the interval of wind speed represented in the data, which were from 10 miles per hour to 40 miles per hour. Hey, I don't know why this pops in my brain, but if they went out to like having you guesstimate what 65 miles per hour, what word is that? Because that's beyond the 40. Extrapolation. Okay, extrapolation is when you are estimating too far outside of your data, and it's not good to do that. That comes up in FRQ sometimes, right? Extrapolation. You do. So if they ask you, like, can you predict what's going to happen at 65? You'd be like, no, that's extrapolation. It's too far outside the data. That would be a good explanation. Okay, so use the computer output above to determine the equation of the least square regression line. Identify all variables used in the equation. I remember on the chapter test, I gave you a problem like this, and you guys did a great job, bless you, of coming up with the equation, but you forgot to define the variables. You have to read what they're asking you to do. You can't afford to lose points for something so simple. Agree? So read what they're asking you to do. So we're going to do y hat equals 0.137 plus 0.24x. You could have also said 0.24x plus 0.137. Like you can do it in the form mx plus b, but please put a hat on your y. Yes, sir? Is that what you're going to ask? Please put a hat on your y because that makes it statistics. You know what I'm saying? They're going to want to see that. And just doing those little extra details that may not get you points, but it may make the difference when a 2.5 needs to become a 2 or a 3. Do you see what I'm saying? When they're making that decision of, is this really a 3 paper or is this a 2 paper when you have a 2.5, you want to put as much detail that's statistically correct as possible. I'd put a hat on your y. Yeah, that makes it statistics. Question? Okay, so y hat is the predicted electricity production in amperes, x is the wind velocity in miles per hour. And I'm literally plagiarizing, and I know students don't like to plagiarize because you're taught not to do that. Scratch that. In statistics, you need to plagiarize. Like you need to rewrite their words to them over and over. They expect it, okay? So it really is okay. One thing that I put on there that I haven't stressed to you maybe is they like the word predicted. When you're writing in context for a linear regression, they want to see the word predicted. It's not an exact y, it's what y is predicted to be by the linear regression. Does that make sense? Like I've seen in the scoring guidelines before where an E becomes a P because they didn't use the word predicted. I know it sounds silly, but they do that. So it's the predicted Y value, Y variable. Okay, part B. How much more electricity would the windmill be expected to produce on a day when the wind velocity is 25 miles per hour than on a day when the wind velocity is 15 miles per hour? Show how you arrived at your answer. I did it completely different than the scoring guidelines did. I think I would still get full credit for it because I showed work and I got the right answer. I took the 25 and plugged it in for X in my equation. Separately, I took the 15 and plugged it into the X in my equation and then just did the difference of those and got 2.4 amperes. In the guidelines, what they did, hold on a second, is they said, well, the difference between 25 miles and 15 miles is 10. You get that? And 10 times the slope, 10 times 0.24 is still 2.4 amperes. So if you were thinking along those lines and you did it that way, they give you credit for that. Questions still? Okay. Part C, what proportion of the variation in electricity production is explained by its linear relationship with wind velocity? What's variation? That's the key word there. That's R squared. Every class has told me that it's standard deviation squared. What are y'all thinking about? That's not variation. It sounds just like it though. That's variance. Variance is standard deviation squared. Variation is R squared. What's R? The correlation. Okay. What is the correlation? R squared right here.
How much the line actually matches.
Here's R squared. Y'all hear me a second? We never use the adjusted one. We never use the adjusted one. Okay, we use R squared. Back to what I was saying. What does it do? Somebody was telling me what correlation does.
It's like how much the line actually matches.
The strength, how strong it is. Okay, so let's talk R for a second, and it is on the Mickey head back there. Talks about what they can be. The R values can be between -1 and +1. -1 is a perfect line that has a negative slope. +1 is a perfect line that has a positive slope. You with me so far? Okay. If it's 0, then it's not a linear relationship. That's the worst you can get. It's like super scattered. Okay. If it's between, and ignore the sign right now. The sign just tells you the slope, right? So if I say between 0 and 0.5, I also mean between 0 and -0.5. Y'all get me? Okay. Between 0 and 0.5 is a weak relationship. Okay, W-E-A-K, weak. Between 0.5 and 0.8 is a moderately strong, if they like to see the word moderate, it's a moderately strong relationship, 0.5 and 0.8. And then from 0.8 to 1, obviously 1 is perfect, but between 0.8 and 1, you have a really strong relationship. You don't have to write the word really, but it's a strong relationship. You okay with all that?
So for 0.5 to 0.8, it's what? Strong. Wait, from 0.5 to 0.8 is moderate.
Oh, 0.8 to 1 is strong. This is R, you're correct. Okay, so R squared gives us variation, and so I just got R squared from the chart. A lot of times on the FRQs, they don't ask it like this. Usually they'll be like, describe what the, what the R squared is. And you would have to write the sentence that you see in part C. So you need to know the sentence. It's like the interpretation of R squared is that it's 87.3% of the variation in Y can be explained by X. That's the sentence they have there. That percentage, whatever percentage your R squared is, that's how much of the variation in Y can be explained by X. That's what you want to interpret that as.
Y can be explained by X.
Mm-hmm. Okay, so you're going to notice on the problems that I pulled up, not one of them says, do a state plan, do conclude, write a hypothesis test. They don't do that. So you're just going to have to clue in, hey, there's a lot of space here, and they want statistical evidence. So they want me to run a test. Okay, I know that feels unfair because why can't you just tell me it's state plan, do conclude? They don't. Okay, so this one says, is there statistically convincing evidence? That's run a test. Okay, that electricity production by the windmill is related to wind velocity explained. So in your state, and you're going to see on all of these that I did, I kept forgetting to do the alpha. I don't know why. Like, did I ever teach it and forget to do the alpha? No. But for some reason, this night, sitting in front of criminal minds doing this, I do. So I kept forgetting to put alpha in. I don't know what the deal was. So you'll notice I put it under state, but don't forget, like, don't make my mistake. So remember, when you do state on almost all of our tests, you need to do 4 things. You need to define your variable, HOHA alpha. State is always 4 things. It's define your variable, that a lot of people forget, HOHA and alpha. Okay, so I defined beta to be my population slope. Let's go over the symbols real quick because one of the classes yesterday, they really had just forgotten all the symbols. So symbols for population versus symbol for sample. You need this? What's the symbol for means? Population is mu, sample is x bar. Okay, what's the symbol for standard deviation? Sigma for population, S for sample or SX. Okay, sometimes you'll just see it as S though. The other thing we test big time is proportion. We test means and we test proportion. What's the symbol for population proportion? P. What is it for sample? P hat. Y'all okay with that? And then this example is slope. For slope, they're going to use beta for the population symbol. For the sample symbol, they're going to use B. On the formula sheet, they also call it B sub 1. They call the y-intercept B naught, like the B with the little O down low. Do you know what I'm talking about? Okay. Does that help? Are there any other symbols you can think of that you need? Can I erase? The only other one we talked about yesterday was sample size. Sample size, if it's lowercase n, it goes under the sample. If it's capital N, that's sometimes used for the population size, but more often capital N means you have a normal distribution. So that one's kind of iffy, but they do sometimes use lowercase n for the sample size. Okay, so back to the test I ran. I did beta as the population slope, and I probably should have done that better, like done it in context of the problem, forgive me. So I probably should have talked about wind velocity and stuff right there. But anyways, HO beta 0, HA beta is not 0. So this is really weird even in my brain, but they're saying if I have beta 0, then I just have a constant horizontal line. But if beta is not 0, then I'm going to have some, you know, as one goes up, the other one goes up. Or if it's negative, then as one goes up, the other one goes down. So they're going to call this linear. When we all agree this HO is linear also, right? It's just they want that relationship as one goes up, the other one goes up, or as one goes down, the other one goes up situation going on. So if we reject, then that means we are going to say it's linear. If we fail to reject, we're going to say, no, we don't have a linear relationship. Now that feels weird, but that's what you do. Okay, so we're going to run a linear regression t-test. So don't do this on your calculator with me, but I want to go show you that you cannot do this one on your calculator. Okay, when you go into linear regression t-test, what do you need to run a linear regression t-test? Lists of data. So when you have computer printout, this is the only one you cannot do on your calculator. All the other ones, even though I showed work on all of them, you can do all of them on the calculator without showing any work. This one you cannot, okay? Because we have computer output, we don't have data.
Is t-test the only thing you run in your regression?
It's always t. So we have means is going to be t, linear regression is going to be t, proportion is going to be z. And then we have chi-squared stuff. Nope.
Great. Always.
Okay.
Anytime we see linear regression, if there's an FRQ, linear t-test.
T interval t-test. Okay. So for my plan, you know that we have to do conditions, right? We need to name the test. We need to do the conditions. Yes? I didn't do that because up here in the scenario, it said we get to something about assumptions were checked and determined to be reasonable. If they say something like that, you can just say conditions were checked and reasonable and move on. You don't have to then prove them. Had they not said that, I would have done what we started calling linear. Remember in the book, it was liner. So linear, independent, normal, equal standard deviations. We put in the A as a class. I don't remember which class did it, but we put in the A to remember to do 10% because they always did independent and 10% together. So we would do assume 10% and random. So you would have to talk about each one of those. So write them all out and then say, yes, you know, the data appears to be linear, and yes, the points were pulled independently, and, you know, we have a normal distribution. The equal standard deviation trips people up. Be very general in describing these conditions because you don't want to say something wrong, but equal standard deviation is just that the line of best fit goes through your scatter plot and they're equally distributed below and above that line. Okay, so you don't have some extreme outlier messing things up. You don't have all your points above the line of best fit, something like that. So they're spread the same. Does that make sense?
For independent?
Independent, like the data was pulled independent, like literally selected independently. You know, it doesn't affect each other, each point or whatever. That the scatter plot looks linear. Okay.
Oh wait, no, I'm just kidding. Normal isn't that how we usually figure it out? If there's at least 30.
Mm-hmm. But we're not going to do that for linear regression. Just write the word down. Approximately normal and move on. So, yes, sir.
Can we go over like which conditions?
Yes, we will within this. Yes, it's definitely built in there. And I will definitely touch on it, but let's keep going. So I did the test statistic by doing the sample minus the population. Regardless of if we're doing Z, if we're doing T, if we're doing linear regression, means, linear regression, either one, you do the sample minus the population on the top of your test statistic. So I'm doing the sample slope, which is from my computer printout. Beta comes from the hypothesized slope. Do y'all get that? I'm plugging in the 0 because that's my hypothesized number I'm using. Y'all get me? And then the bottom is the standard deviation from the chart. So notice that I'm using my B to be 0.24 and I'm using my SE, my standard deviation, to be 0.019. That is standing for the standard error. That is your, excuse me, that is your standard deviation. Are y'all okay with my setup? Okay. So calculated this, got this, went to my calculator to do TCDF, and I remembered to double it. Why am I doubling it? It's two-tail. Why is it two-tail? Anytime our alternative hypothesis is not equal to, we need to double if we're working it out by hand. This may be the only one you have to work out by hand, guys, because you're probably going to do all the other ones on the calculator. Okay, we have to double it if it's a not equal to. So I did 2 times the TCDF of my lower bound is my test statistic, upper bound is infinity. It wouldn't be enough to put 10, right? Not when you have a T of 12. So like you can't put 10 as your upper bound. So I went out and put 1,000. Degree of freedom is the sample size minus 2, only for linear regression. Okay? So if you write, go ahead.
You always use TCDF?
For T's, you use what for Z's?
Normal
Normal CDF. For linear regression, it's going to be TCDF only. Yes, sir.
So how do you like figure out what tests you're taking? So like is there a keyword for
Which test we're doing, like this right here? I mean, it's just a computer printout and talking about slope, and like it has to be linear regression, you know? Means is going to have to be a t-test. Proportions is going to have to be a 1 proportion z-test. Okay, but we'll see all the different ones. And then we'll have like categories is chi-squared. So you'll see them if we can keep pushing through. What I want to point out to you about this z-score, I'm sorry, this p-value is that you cannot have a p-value bigger than 1. So you're going to look at your calculator and it's going to say 7.88. And some of you will happily write down 7.88 is greater than 0.05, so I failed to reject. And that is wrong, wrong, wrong. Like it's going to look like you know nothing about statistics because your p-value cannot be bigger than 1. What does 1 represent in a p-value?
the entire probability?
100%, right? So how can you have 788%? That doesn't make sense. Okay, so 1 represents 100%, so your p-value has to be less than 1. It can be 0.95. That's crazy, but it can be. But it can't be 7.88. So do y'all see that it's going to have like e negative 12 at the end of it on your calculator? So you're going to just call that 0, okay? Because it's like 0.11 zeros and then the 7. Like it's a really small number. So we're going to say that's less than 0.05. We reject HO. And then here's something that the publisher does different than I've noticed the scoring guideline does. So let me kind of tell you this. I don't think it's a big deal, but we really need to write correctly. If you reject, say there is convincing evidence, blah, 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 context or problem. If you fail to reject, say there is not convincing evidence, blah, 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 context or problem. Okay, so I was always, because the published, like our textbook that we use, they always say there's convincing evidence, and then they say which one we're proving. The scoring guideline, and I don't think that would be wrong, like the AP grader would read through it and they would be happy with your explanation, but I just feel like to really match what they're doing, let's stick to reject. You say there is convincing evidence, fail to reject, you say there's not convincing evidence, okay, and do it that way. So this one we're rejecting, so we're saying this is not true, this is true. So there is convincing evidence that beta is not equal to 0. So if we failed to reject, we'd say there's not convincing evidence that beta is not equal to 0. So then the electricity production by the windmill is not linearly related to wind velocity if it were failed to reject. Yep. Okay, so before I move on to the next one, I want to talk to you about confidence interval. It's not asking us to do that, but I want you to know the setup of it. They're always on the multiple choice, right? Do y'all agree? Okay, so you have to know how to come up with the confidence interval. And hey, they may ask you on an FRQ to do one. So if we had to do one, You would do your slope plus or minus your t star times the standard error of your slope. This is the easiest one to do because 2 out of the 3 numbers come from the printout. The slope is literally just the slope. It's also called the point estimate. What else is it called? I don't know. It's called the point estimate sometimes. But anyway, it's 0.24. The standard error we're going to use is 0.019. So you have your 0.24, you have your 0.019. Where did I get the 1.7139 from? Okay, you have to inverse t of whatever percentage they give us. So I just made up an example. Like, what if we were doing a 90%er? We would do second verse, inverse t. If we were doing z star, you would do inverse norm, right? Inverse t for t star, inverse norm for z star. Okay, area. I want you to get in the habit of just doing parenthesis 1 minus whatever percentage you have, close parenthesis divided by 2. Don't mess with the decimals and worrying about making sure you move it enough times and all that. Just get in the habit of doing that. 1 minus whatever percentage we have divided by 2. What's the degree of freedom? 23, because it's sample size minus 2. And so that's where I got that t star from. And then the other thing I did is I just did each one in my calculator. 1 time minus gave me the 0.2074, and then 1 time with plus gave me the 0.2726.
That's for confidence interval. We're just the slope from the chart, and then use the inverse t star and the standard error from the chart.
Yep.
Okay, so it's inverse t for t star and inverse norm for
Z star. Guys, if they asked you to do a confidence interval, do you know that that's also a state plan to conclude?
yes.
Confidence intervals are also state plan to conclude. And it won't say that. But if it said construct a 90% confidence interval, you would do state. We want to construct a 90% confidence interval to blah, 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 blah. Plan. I'm going to do a linear regression t interval. Conditions. Linear. Do. Show the work I showed. Conclude. We are 90% confident that the interval from 0.2074 to 0.2726 captures the true slope of the, remember all this? Okay.
Are we gonna ever like have an FRQ where it's like 2 state plan to concludes?
Yes.
Oh.
As I went through all of these, it seemed like it was always 3, 4, or 5.
But there's 2.
There's usually 2. Could be 3,
Whoa.
but there's 2. No, I've never seen 4. But it was always number 3, 4, or 5 for some reason. So especially pay attention to 3, 4, and 5. Number 1 is usually a SOX problem.
Do you look at like, you know how like some AP teachers are like, do the last FRQ first?
You do what you do. I feel like if you go straight to number 6 on the AP stats, that you might start crying. So just go ahead and leave it till the end and do your absolute best on 1 through 5. Just do your best on 1 through 5, and whatever time you have left, attack number 6. Yes, it's worth the most, but hey, y'all, listen up a second. Yes, number 6 is worth the most, but it's not worth doing so much time on that one that you don't even get to attempt 1 through 5. Do you see what I'm saying? Because 1 through 5 are going to be so much more doable. In AP Stats, number 6 is called the investigative task. And even our best of the brightest last year said they had to stare at it a while to make any sense of it. So I'm not trying to scare you, but number 6 is supposed to make you stop and think. So I don't want you doing that before you do 1 through 5. Me personally, you do what you know is going to be best for you. Okay, guys, come on, we got to move on. So a random sample of 200 students were selected from a large college in the United States. Each selected student was asked to give his or her opinion about the following statement. The most important quality of a person who aspires to be the president of the United States is a knowledge of foreign affairs. Each response was recorded in one of 5 categories. Right there, categories should tell you maybe this is a chi-squared. Because when we deal with categories, isn't it chi-squared? Agree? Typically, okay? The gender of each selected student was noted. The data are summarized in the table below. Is there sufficient evidence to indicate that the response is dependent on gender? Dependent, that's a key word. Doesn't it go with independent? And don't we have a chi-squared test for independence? Y'all get me? Okay, so provide statistical evidence to support your conclusion. Hopefully you look at that and go, oh, I can put that in a matrix. Do you do that?
Yeah.
Okay, good. So what is the size of our matrix? You should do this with me. We haven't done it in a really long time. Okay, second matrix. Okay, over to edit. Okay, my B should not be there. Oh, well, I'm going to leave it. You should not have a B, right?
Wait, what if we do?
So Second matrix, 2, enter, 5, enter, fill the data in. You will not have a matrix B unless you have something else, right? Run before. But how do we create matrix B? By running the chi-squared test. So we have to run the test before we look at matrix B.
Wait, hold on.
I'm holding on.
I'll write that down.
Do you know anybody that can show you how to do like good sheets online or something for the calculator, the tests, like plug in stuff?
You can just Google, but you have to have the cord, and you can do like TI Connect and like type stuff. And what y'all need to do if you really want to put stuff in your calculator is not do it because it's against college web. Okay, so when we're doing a chi-square test for independence, we need to make sure our null hypothesis is no association, and the alternative is there is an association. Okay, test for independence, the one with the matrix, HO has to be no association, HA is an association. Okay, so I said there's no association between the response and the gender because you want to use the context of the problem. And then I, in parentheses, just added for my own brain so that I could answer their question. If there's no association, then doesn't that mean that response is independent of your gender? Okay, and then if there is an association, then that means that your response is dependent on if you're male or female. Like it is dependent on your gender. Okay, so don't forget on your state, you also need to define your significance level. Alpha's 0.05. Yes, ma'am?
So I think that was one of the questions we had on like a test recently where one of the cell counts weren't at least 5. Now, if one of the
They're not going to do that to you.
Okay.
They cannot do that to you.
Okay. So
And it's not the observed, it's the expected that has to be. So the observed may not be 5, but the expected has to be.
Yeah.
Matrix like this.
That's why I get confused. The observed.
Observed can be whatever. It's the expected that has to be at least 5. Keep going, keep going. Plan. Okay, to the plan. We have to name the test. We have to list all the conditions, okay? So chi-square test for independence, if you just called it a chi-square test, I think you would be fine. But why not throw in the for independence when they're using the word dependent in the problem? Do you see what I'm saying? Like you can be confident that it's for independence. What's the other one we do? Goodness of fit, but also chi-square test for homogeneity. Okay, but again, if you don't feel comfortable writing that word because maybe you forgot how to spell it, then don't write it. Just write chi-square test. Move on with your life. But we will do a goodness of fit problem. If we get to it, it's at the very end, but we won't do a homogeneity problem, okay? But it's going to be run exactly the same, okay? So anyway, random 10%, expected counts are all at least 5. Where did I get this from? Once you run it, so you did stat test up to chi-squared, which is C, okay, and you go down to calculate. Once you do that, it creates your matrix B. So you go second matrix, over to edit, down to B, press enter, and you'll see my matrix B. And you literally write that down and say, look, these are all at least 5. Then you're not going to be running that test. You probably made a mistake. Go check your type, like calculation, like your input. Go check what you typed into there, because it should be. Okay, so when I ran the test, you'll notice that I did get those values that I have written under my do. I got chi-squared, let me get this to go, calculate first. I got chi-squared was 8.9226. I got the p-value is 0.0631. Excuse me, degree of freedom is 4. How did they come up with degree of freedom was 4? Because sometimes there's a multiple choice question that's like, how do you get this?
Rows minus 1 times columns minus 1.
Rows minus 1 and then times columns minus 1. So you subtract 1 from each of them and then multiply what you have left together. So 5 minus 1 is 4, 2 minus 1 is 1, 4 times 1 is 4. Yes, sir. I wouldn't for a chi-squared, me personally. I think I showed you guys you could put like input matrix A and then you list the matrix A that's up and above. Like
You just write like parentheses calculator.
you could do that. But I think on chi-squared, you don't really get graded for work. I would say if you're done with all 6 of them, especially if you're an AP Bio student and you really know this stuff, go back to a chi-squared problem and actually show the work for the chi-squared where you're doing like observed minus expected squared over, what is it, out of,
Wait, so when you're on.
what is it, AP Bio people? Come on, Rachel.
I thought it was possible.
What's the question?
I don't even think it's on our formula sheet either.
Observed minus expected squared over observed.
Yeah, it's over expected. It's on our formula sheet. So, but did y'all hear what I said though? If you have time at the end, I don't think it's worth it because I don't see them docking you for not. But just to be safe and get that 2.5 to become a 3, if you have extra time and you had a chi-squared, the formula is at the bottom. It's the sum of observed minus expected squared over expected. You could just show the work for each one. I wouldn't do it though unless I was sitting there bored. Do y'all see what I'm saying? Yes, ma'am.
So once you learn these six accounts, how do you get back to seeing where the exports?
Well, you would have written those down first, probably. I personally would have, and then went back and filled in my expected, but you have to run the test again in order to see it again. So P is 0.0631, failed to reject. There is not sufficient evidence that the alternative is true, right? Y'all get me? If I'm failing to reject, there's not sufficient evidence for the alternative. So we say there's not sufficient evidence to indicate that the response is dependent on gender. You could also say there's not sufficient evidence to say there's an association between response and gender. But I really wanted to be careful to answer their question, and they were asking about dependence. Do you see why I worded it that way?
Miss Hall, before you go to that, can you go back to the last, the one before that, just really quick so I can write something down?
Or like candlelight.
Okay, got it.
Okay, guys, we got to speed along. Let's go, because I want to cover as much as I can with you. Okay, a humane society wanted to estimate with 95% confidence the proportion of households in its county that own at least one dog. Interpret the 95% confidence level in this context. Okay, this was a real FRQ. And by the way, I did put the years on them on purpose in case you wanted to go back and look at the real question. Okay, I did sometimes only take part A when there was a part B, C, D. Like I was like, oh, I just want to talk about this part with them. But you can go back to these if you want. But anyway, we learned two things about interpretations on confidence intervals. We learned to interpret the confidence interval itself. And isn't that always the conclusion on the state plan do conclude for an interval? Okay, so what's that sentence? It's not what they're asking for. We are 95% confident that the interval from whatever number to whatever number captures the true proportion of all households who have at least one dog. Okay, that's the confidence interval interpretation. The confidence level,
When we interpret the confidence interval, don't we always do captures the true population?
population mean or population proportion or whatever the data is. For confidence level, there's some key things you need to remember to say. You need to say in repeated samples of the same size, like you're going to do this over and over and over, and all the samples you pull have to be the same size. You also need to say in the long run. They like that word, those words for some reason. I don't know why. So in repeated samples of the same size from the population in the long run, 95% of the intervals would capture, and then we go back to what we say in the interpretation of the interval itself. We capture the actual population proportion of households in the county that own at least one dog. But it's the in repeated samples of the same size, in the long run, 95% of the intervals would do what we want it to do. Okay. The Humane Society selected a random sample of households in its county and used the sample to estimate the proportion of all households that own at least one dog. The conditions for calculating a 95% confidence interval for the proportion of households in this county that own at least one dog were checked and verified. So I don't have to list all the conditions. Y'all catch that? And the resulting confidence interval was this plus or minus this. Okay, 0.417 is our point estimate. What is it also for this problem? It's not B for slope, so what is it? It's P hat. It's our sample proportion, yes? What's after the plus or minus? Because we're going to need this in the next problem. Margin of error, okay? Everything after the plus or minus is the margin of error. Margin of error is made up of the critical value times the standard deviation. But since it's one number, those two things have made that one number. And that's our margin of error. Do y'all follow me? Okay, because we're going to use a little bit. You get where I got my interval from?
So it's critical value of
Critical value times standard deviation would give you 0.119. We can't see it from the 0.119.
oh, so just to do that, you just have to know that whatever it was.
Everything after the plus or minus, if they've already calculated it, it's the margin of error. Okay, so do y'all get where my 0.298 and my 0.536 came from? I just subtracted and added and got those numbers. Okay, a National Pet Products Association claimed that 39% of all American households owned at least one dog. Does the Humane Society interval estimate provide evidence that the proportion of dog owners in its county is different from the claimed national proportion? Is 39% in our interval? Yes, so it looks like the county, like 39 does fit. So we say no because they're asking, is it different from it? Isn't that kind of backwards the way they're asking that question?
Yeah, everything after the what is the margin of error? After the
Plus or minus. The plus or minus symbol.
So if the number is in the interval,
Then it's a plausible value. Like it should be right. But if it's outside, then it's not a possible value. And so I said no because 39% is in the interval. Then there's not evidence that it's different from the national proportion or whatever. So they asked that kind of weird. Okay, so here's the problems that you guys really don't seem to like, and it's solving for the sample size. And you know it's going to be at least one multiple choice, at least, right? So I'm going to over there. Okay, so using that formula instead of the way I have it on the board, we need to do, according to that, n is equal to p hat times 1 minus p hat divided by, I have MOE for me stands for margin of error, divided by critical value, and then all of that squared. You are going to have to remember how to find the critical value. Anytime you're doing sample size, and I know this is weird for us, it doesn't matter if it's proportions or means, your critical value is always Z star. Always. Can't be for margin of error, for solving for a sample size. Okay? It can't be T star when you're solving for a sample size because then you would have to have DF. And DF would just be add 1 to it and you have your sample size. Do you see what I'm saying? So we use Z star as our estimator, like as our critical value that's just an estimate because we can't get T star. So
we'll have formulas for the same errors. Yeah.
okay, so what's our p hat from this problem? I'm going to do it over here. Let me back up a second. What's my Z star? It's a 95% confidence interval, so you guys have it memorized that it's 1.96, right? But if I needed it, for some reason I couldn't remember that, my brain's fried on the day of the test, then I go inverse norm, 1 minus the 0.95, and then divided by 2. Go with me?
yes.
That's going to give you the Z star. You just put whatever percentage you're running, and you'll have it. Okay, so that's our 1.96. So how I'm going to put this in my calculator, I'm going to do a big fraction is alpha y equals, not your best friend now, and stats, come on now. That's like the best. My p hat is 0.417, so I have 0.417 and then 1 minus 0.417 on the top. I want to go to the bottom, and I'm going to put parentheses, and then I'm going to put another fraction because I want to put the margin of error on top. They gave us a margin of error to be 0.119. Where did I get that from? I got it from the plus or minus up there. They didn't like say it in the scenario. You had to know that was the margin of error. Tricky, tricky. Okay, Z star we found out was 1.96. We come off of it. We square it. I meant to put a parenthesis. I don't know if that'll matter. Let me go fill that in. And you get 66. Guys, even if that came out to 65.1, you have to call it 66. You have to round it to the whole number for solving for a sample size. I can't tell them to go get 65.95 households. Okay? I have to go up to the 66 to capture the full margin of error that they want. Y'all okay with that? Okay, next one. A bottle filling machine is set to dispense 12.1 fluid ounces into juice bottles. They haven't said it yet. They're going to say it, but what kind of data is that? Is that proportion? Is that means? Is that categories? What is that? That's means. It's the average amount they're putting in the bottle. So I know I'm doing some type of T stuff because I'm dealing with means, okay? To ensure that the machine is filling accurately, every hour a worker randomly selects 4 bottles, sample size is 4, okay? Filled by the machine during the past hour and measures the contents. If there is convincing evidence that the mean amount of juice dispensed is different from 12.1 ounces, or if there's convincing evidence that the standard deviation is greater than 0.05 ounce, The machine is shut down for recalibration. It can be assumed that the amount of juice that is dispensed into bottles is normally distributed. That's big. Okay. Our sample size is not big enough. What's our sample size? 4. What do we need it to be? 30. It's not big enough. But they said we get to assume it's normal, so we're good. CLT doesn't have to happen. Is that making sense? During 1 hour, the mean number of fluid ounces of 4 randomly selected bottles was 12.05. Standard deviation was 0.085. We're given a bunch of information. 12.1 is our mu. 0.05 is our sigma. 12.05 is our x bar. 0.085 is our sample standard deviation, so either S or SX. Are y'all okay with all that? We're given a ton of stuff. So I had students yesterday, I don't have a good answer for you. They're like, but Ms. Hall, if we have the population standard deviation, can't we run a Z-test? I think they'd give you credit, guys, but I don't know. Like, I don't know what the AP grader would do in that. We're seeing if we need to recalibrate the machine or not. So we're seeing if the 12.1 is still good.
I would have never
So
thought
why
of
is
these
it
details.
why these tests?
Because it's means, right. It's hard. I wish we didn't have the 0.05 is my point, because then y'all would not even question whether we're supposed to do Z or T. Just please do T regardless, because I've never seen them ask you to do a Z test on means. They just don't
That's all-
ask you
yeah,
to do
that's
that. But they always want to give you a multiple choice where they ask you why would you do a Z test in this situation? It's because I have the population standard deviation. So here you want to do a Z test because they gave us the population standard deviation. Let's not. It's what they want it to be. It's not necessary. So anyway, I'm going to move on. I'm going to do a T-test because it's means, okay? So remember, under your state, we need to do 4 things. We need to do alpha level, HO, HA, define your variable. Okay? So our variable is mu because we're dealing with means. Remember to always use population symbols in your state, okay? So we're saying mu is the mean amount of all juice dispensed. The null hypothesis is that the machine is good, and so mu is exactly 12.1. The alternative is that it's different from 12.1. They didn't say greater than, they didn't say less than for the mean. Now they did for the standard deviation, and we'll get to that later. But for the mean, they said if it's different from 12.1, we're recalibrating. So do y'all understand why I did not equal 2 there? Okay, and then alpha is 0.05. Plan, I'm going to do a T-test. We get to assume the conditions are met. If they were not met, then what would we have to, because it said that somewhere on there, assume conditions for inference are met. But if they didn't, what would our conditions need to be?
Random 10% and
Okay, so random, 10%, and large sample. For means, we say large sample. For proportion, we say large count. It's CLT and has to be greater than or equal to 30. As I was writing up the solutions, I was looking at different scoring guidelines, and I kept seeing them throwing in independent as well. Please just, if you can remember, put independent on everything except test for independence. That would be kind of stupid, right? To be like, a condition is it's independent. Oh, but I'm testing if it's independent. Like, that doesn't make sense. But all the other tests, it's going to be fine to say the sample, each part of the sample was pulled independently. That's fine. There's nothing wrong with saying that. Because I don't want you to be docked for not saying it. Usually they put 10% and independent together. Okay, so for means, and it's written on the board here, for means, and actually for proportions as well, we're going to say random, 10%, and independent, no matter what kind of test we're doing. Random, independent, 10%, and explain it, okay? Usually for random, you get to say, like, stated in the problem, right? Most of the time. Okay. For means, though, for a large sample, you want me to write that? Large sample, we have to have CLT. We have to have n is greater than or equal to 30. Or it has to tell us it's normally distributed. And if neither one of those things are true, then you graph it to show there's no skewness and outliers. Yes?
Question. We used to have to do that on the test. I didn't know how to find the box plot.
I'm going to show you. We're going to do an example if we can get to it.
I just drew like a box plot. It's just what I thought.
Okay, I'll show y'all one if we can get to it. This one is called large samples. So if you're doing proportions,
Wait, they're both large samples?
I'm sorry, large count, large count, large count. Thank you for catching that.
Killing me, Smalls.
You're doing great.
For proportions, it's large counts. N times P has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10. Okay? We will do an example of that if I can, like, speed through this. Okay.
If they say large counts for large sample, that's just backwards. No, that's
They're not going to say it. You're supposed to say it. Means, you need to say large sample. Proportions, you need to say large counts. It's going to be a fill in the blank FRQ. Don't y'all wish? Okay, so we did the plan. Okay, now do. So for do, you're not going to do what I did more than likely. Okay, more than likely, you're not going to show all that work. I'm not mad at you. You're going to do it on the calculator. So you're going to go stat over to t-test, which is number 2. Do you see it? Yes?
Yes.
Do we have data or do we have stats?
Yes, sir.
We have stats. You're not going to be on data unless you have a list of numbers. Okay, so we're on stats. What's our mu naught? What happened? 12.1, right? What is our x bar? What is our SX? Not sigma. Isn't it 0.085?
Yeah.
What's our N? 4 bottles. If we were working it out by hand, you're going degree of freedom on me, aren't you? What's our degree of freedom? 3, which is sample size minus 1. But I'm going to use a calculator so I don't have to think about that, okay? What's that?
Yes.
Calculator does.
Yeah, it prints out.
You only need it if you're going to work it out by hand. Okay, we're going to select not equal to, and we're going to calculate. And that's where my test statistic and my p-value are going to come from. They're close enough, agree?
So for the not equal to, less than or greater than, would kind of get confused on like, not the not equal to, because that's pretty self-explanatory. Let's like, how would they word it if you would want to be less than?
If they said we're going to shut off the machine if it's overfilling the sodas, then my HA would be greater than. If we're going to shut off the machine if they're shorting our customers, then you're going to less than. It's always for HA. HO is equal no matter what. Okay?
And then for the data, so you do stats for that, but what would be like the situation for the data? You said like
They would give you a list of like, I went to the machine and these are my 20 results of when I measured the cup.
Whenever I see that, but it's like, it'll be like a list.
List of numbers, yep. You'll see one actually in just a second. I'm going to skip the dot plot thing because it's not worth losing the other ones. Like I pulled it because it's once on like 10 years that I've looked at. We did daily checks like this. I'm going to move on. Are y'all cool with my conclusion? Can I, because I want you to see the scenarios more than I want you to see my write-up. You go back and look at these if you want more detail. This would be a list of data. But we found out yesterday when looking at it, I didn't even think about it this way. You can run it as data or you can run it as stats because they also gave you the mean and standard deviation. You can run it either way. And I ended up running it both ways and got the exact same answers.
What's easier?
Honestly, if they've given you the mean and standard deviation, that's going to be a lot quicker for you. Agree? Okay. But look what I have to do.
What is that?
Graphs. Why am I graphing? Because CLT is not met. Okay. It's a what?
Problem.
These are the ones that always do.
Like, we just went to a different FRQ.
Yes, the different FRQ. A large pet store buys the identical species of adult tropical fish from 2 different suppliers, Buy Right Pets and Fish Friends. Several of the managers at the pet store suspect that the links of the fish from Fish Friends are consistently greater than the links of the fish from Buy Right Pets. Random samples of 8 adult fish from Buy Right and 10 adult fish from Fish Friends were selected, and the links of the fish in inches were recorded as shown in the table below. Do the data provide convincing evidence that the mean length of the adult fish of the species from Fish Friends is greater than the mean length of the adult fish of the same species from Buy Right? So I define my variables as mu F and mu B. Mu B is all the fish from Buy Right, and then mu F is all the fish, the mean length of the fish from Fish Friends. Does that all make sense? Go ahead. Alpha is 0.05. And then we have HO. We think that the fish are the same size at both stores. So I'm going to do mu of B is equal to mu of F. There's no difference between the stores. But the little thing that we're testing for, it says Fish Friends is actually greater than Buy Right when you're looking at the average length of their fish. They have bigger fish at Fish Friends. So does the mu B less than mu F make sense? Because F is greater than B when you read it backwards. You see it? I see the eyes back there. You good? So my plan is to do a t-test, but it's 2 sample this time. 2 completely separate samples. Random independent 10%. You want to talk about each one. I would probably need to elaborate on independent and say that the fish don't affect each other or something like that. Like the length of one fish doesn't affect the length of the next fish that they pulled. Yes, sir?
Is alpha always 0.05 or does
unless they tell you otherwise. Yes, sir.
For random, do you have to like write a sentence or just say random and say?
Usually it's just stated. They pulled them randomly.
Yeah, I know, but do you have to say like it isn't a random?
You're going to see one in a minute that doesn't specifically say random, but it says they tossed a coin. And so you'll see that I wrote random, and in parentheses, I wrote toss a coin, even odd days. Like I explained that the treatment was given randomly.
You have to say like it is a random sample.
Stated is okay. You can say
What do you
stated.
Like if you shorthanded and just put random, are they gonna count?
I would at least put stated because they want some proof that you know it's random.
What do you have to write for it again?
I would just say that the fish link doesn't affect other fish links or something like that. Each fish pulled is, you know, not dependent on another fish. Okay, but guys, back to this, please. We have two samples. We have a sample of 8. We have a sample of 10. Neither one are big enough. Agree? Okay, so what I did, y'all do this with me if you are uncomfortable with how to get box plots. Okay, box plots to me is the easiest one to do because it shows outliers and skewness. You just look at the whisker, you look at, you know, you can do a histogram, you can do a dot plot. I'm gonna do a box plot. And they don't care what kind of graph you do, you just have to do a graph. So in list 1, I'm gonna put 3.4. I'm gonna type these in really quick. I wish I had hours with y'all. I'm sorry. 2.7, 3.3. And then in list 2, I'm going to put the fish friends data.
You know, they say fish friends not good, really.
Okay, why am I doing this again? I'm doing this because it doesn't meet the sample size requirement. Y'all with me? Okay, so I'm going to go to second y equals. I'm going to turn on the first plot. I'm going to make sure that the type is on the box plot that has the dots. That's going to show you if you have outliers or not. Okay?
Third one, fourth one. Is that the one you selected? Fourth one?
Uh-huh. Yours looks different on your calculator, though, because it has 2 rows of graphs. What's that? Then it'll be the 4th one. Okay? I'm going to do second one to make sure it's graphing L1 for me. Second one to make sure it's graphing L1 for me. Frequency is not L2 this time because I'm graphing them as 2 separate sets of data. Okay, so I'm going to go back to second y equals. I'm going to go to number 2. I'm going to turn it on, and I want this one to also do the box plot, but I want it to do it of L2. Y'all get me? I'm going to have 2 separate box plots. Okay, I'm going to never hit the graph button on the statistics test. What button do we push? Zoom 9. Okay, you have to give the values. Where do I get the values from? I hit trace. Look at trace. Okay, the min on that one is 2.7. The Q1 is 3.15. The median is 3.4. The Q3 is 3.65. The max is 4.1. It won't keep going to the right, so you have to arrow down to get to the red one. And then you see I can toggle through to get those values as well. That's where I got the values from. You have to show the values. Yes, ma'am.
I can just draw a box plot and then use the values from the data given.
That's going to take you so much more time, but you go with your bad self. If that works for you, go for it.
So that's
Yes, go for it, but it's going to take you longer. It's going to take a lot more thought process to get in order and all that good stuff as well. Yes, sir.
So why do we have to draw graphs?
Because our sample size does not meet the 30 thing. If it were 30, we'd be good to go.
Okay, but like, what does it prove by drawing out the graph?
I don't have outliers and I don't have strong skewness, so I can assume normality and I can continue with my process.
Okay.
If I had outliers, then I did something wrong because I can't even do the test then.
Okay.
I believe it.
Wait, how do you get it to show the values?
Trace. Your button is trace. And then you hit right and left to toggle back and forth, and you hit down to get to the other one. Okay, guys, let's keep going. So that is not how you're going to run it. You're not going to work this out the way I did. That's beautiful, but you're not going to do that. So now that you have the data in, you go stat test. This is a 2-sample t-test. It is not number 2. This is number 4. Is that right? I'm going to do data and set of stats first. Like I told you already, you'll get the same answer. It doesn't matter. So I put my data in list 1 and list 2. Frequency is 1 on both of them. My alternative hypothesis is less than, right? Okay. And then leave it on no for pull. Don't change that ever. Go to calculate. And that is how you get the negative 0.2587 for the t. And then my p-value is 0.3996. Working out by hand, I got 0.4016. It's so close. It's 40% either way. It's failed to reject either way. Do you agree? Write your deal. Can I move on? Okay. Investigators at the U.S. Department of Agriculture wish to compare methods of determining the level of E. coli bacteria contamination in beef. 2 different methods, A and B, of determining the level of contamination were used on each of 10 randomly selected specimens of certain type of beef. The data obtained in millimicrobes per liter of ground beef for each of the methods are shown in the table below. Is there a significant difference? This time we need to do the difference. We don't even want to look at them separately. We want to look at their differences. Are you with me?
Yes.
Okay. Not always. Why is this a match pair t-test looking at this data? Because specimen 1 had to go through both treatments. So specimen 1 is its own match. Does that make sense?
Yes.
Okay. Is there a significant difference in the mean amount of E. coli bacteria? And mean, by the way, we know we're doing difference of t, right? The t-test, difference of means for t-test. Possibly, yes. Detected by the 2 methods for this type of beef. Provide a statistical justification to support your answer. So in my state, I need to define the variable. I need an alpha 0.05, HOHA, okay? If the methods do not have any effect, then wouldn't my mean difference be 0 for their E. coli count?
Yes.
Okay? But I think they're going to be different, so my alternative is that they're not equal to 0. Does that make sense? Okay, I'm not saying method A is better than method B or method B is better than method A. I'm just saying they're different, not equal to each other. Okay, so the way I want to do this on this calculator, please do this with me. I know it's a lot to type. I'm going to clear. Hey, I learned something. We'll give Barrett credit. Barrett Vaughn in my 4th period. If you watch this, he's getting credit. He taught us yesterday, y'all aren't going to want to clear list by doing second plus 712, are you? Because you don't want to lose stuff you got in your calculator, right? Second plus 4. Look at what second plus 4 says. Clear all lists. Press enter. Go back to your list and now it's done. So then you don't have to go through my process of clearing if you don't want to. I would just go up, hit clear, hit enter. Anyway, this is going to take a minute. So you guys type this in your L1, L2. I'm going to go to the computer and do it. Excuse me, because it'll be faster for me. Type these in really quick. List 1 and list 2. Okay, so on a test like this, you're timed, and you don't want to sit there and take the time to go, what's 22.7 minus 23.0? What's 23.6 minus 23.1? We don't have time for all that. Watch what I'm going to do. I go to L3. I go up to L3, and I tell it to do it for me. I want you, calculator, to take L1, and I want you to subtract L2. Do you follow what I just did? Press enter. It fills in the difference for you.
Wait, how did you get the L1 minus?
Arrow, you have to arrow up to L3. You have to do second 1 minus second 2 and then press enter. But guys, now you have to remember everything we're doing, we need to do it on L3. Do we have enough data? Nope, because we don't have a sample size of 30, do we? We have a sample size of 10. So I graphed L3. Okay, so I went second, y equals, turn my plot on, go select L3, so second 3, make sure I'm on the box plot. I also want to go and turn the other plot off because it's not the data I'm dealing with anymore. Okay, so zoom 9, and that's where I got that graph from. And I hit trace, and I got my -1, -0.1, and so on. You got to put the values on your graph. So it is approximately normal. There's not strong outliers. We're good to go. Stat test, t-test this time. I don't have 2 samples, right? I have 1 sample that went through 2 treatments. Okay, so stat test, we do have data. What is our hypothesized mean? 0, because it's the mean difference. Okay, our data is in list 3 for this test, right? So make sure you change that list to L3. Our alternative hypothesis is not equal to, and we want to go down to calculate. And so you should get about 1.4563 for your t. You should get about 0.1793 for your p-value. I had just realized that on all of these problems, I have not done a good job of calling that p-value. Be careful of that. If you're doing it by hand, you're not saying p is equal to, you're saying TCDF. You see what I'm saying? So make sure you label your stuff. Sorry about that. I have been doing the t's, but I haven't been doing the p's. But anyway, make sure you tie it back of why you're making the conclusion. In your conclusion, you want to do your fail to reject. Can I move on? Okay. This wasn't supposed to stress you out. This was supposed to make you feel better. Not making you feel better? Uh-oh. Should I stop?
No.
Some boxes of a certain brand of breakfast cereal include a voucher for a free video rental inside the box. The company that makes the cereal claims that a voucher can be found in 20% of boxes. It's going to go on to say proportion in a minute, but I need you to know that percentage is proportion. Do y'all agree with that? 20% are doing something. That's the proportion 0.2 of all the stuff. Okay, that is a proportion. However, based on their experiences eating the cereal at home, a group of students believes that the proportion of boxes with vouchers is less than 0.2. This group of students purchased 65 boxes. So that gave us a lot of information. Our P is 0.2, our N is 65, our alternative symbol is less than, because they think it's less than what the company claims. Do you get all that? That's a lot of information right there. To investigate the company's claim, the students found a total of 11 vouchers for free video rentals in the boxes, 65 boxes. So our P hat would be 11 out of 65. You with me? So P is 0.2, P hat is 11 out of 65. So we want to define P, our population proportion. It's the proportion of all the vouchers in the cereal. We want to do alpha is 0.05. We have HOP is equal to 0.2. HAP is less than 0.2 because that's what the kids think. The students think that. This is a 1 sample z-test for proportion. If you called it a 1 proportion z-test, I think you'd be fine because that's what the calculator calls it. But you'll notice in the scoring guidelines, they're a lot more specific, okay? But if you just said 1 proportion z-test, you should be fine. Random 10% independent. So random, it did say, or stated to be assumed up there, that it's assumed that they took their 65 boxes randomly off the shelf. Obviously 65 boxes is less than the 10% of all cereal boxes. And then you have independent, each box is said to be independent of each other. And then you have to prove your large counts. This one does work, okay? Large counts for proportions, large counts for proportions. You're gonna, pay attention to this real quick. You're gonna use P, not P hat. Okay, if you're proving large counts for a confidence interval, you do use P hat. But if you're running a test, you should be using P, which is the same thing you put in your HO and HA. So I'm not going to use 11 over 65. I'm going to use 0.2. Y'all follow what I'm saying? P hat for confidence interval if you're doing NP and 1 minus P, but P for testing. Okay? Yeah. Okay, so that's what I did here. It did work, so I didn't have to graph it. And then on my calculator, do you know what test I would be doing? It's not z-test. We should not, yes, we should not ever be doing number 1. We just shouldn't. It's a 1 proportion z-test. Because the very first z-test, if you look at it, it wants means. We don't have means, do we? Y'all follow me? So we should be doing number 5. Our P naught is 0.2. Our X is 11. Our N is 65. Do you follow what I have entered there? Okay, we need to be doing less than for our symbol. Okay, so my Z is negative 0.62. My P value is 0.2676. And then I make my conclusion and I'm good to go. Everybody cool with that one? technically 11:15. Apes told their kids 11. So, but 11:15 is what the email says. You're supposed to be at the gym at 12 and plan to sit there and wait a while
Eat lunch, get out, go eat lunch, and come back.
and be at the gym by 12.
Oh, we get out at 11:15, go eat lunch, come back, be at the gym by 12. We don't need to be there any earlier than 12, just, okay.
More than likely, y'all are going to stand there and wait for the world history people to get out of their test. Is it world history? World literature? They get out and they get a chance to go eat lunch. Last year, we stood there for about an hour waiting for them to get out and get lunch and get back in so that y'all could start the test. But still be there by 12 in case it's more streamlined this year, because I don't want them to start without you. Okay? For many years, I'm going on to another one. Y'all ready? For many years, the medically accepted practice of giving aid to a person experiencing a heart attack was to have the person who placed the emergency call administer chest compressions. They're going to call this CC, chest compressions. You know what they're talking about? And MMR. MMR would be mouth-to-mouth resuscitation. Did you know that research shows that it's better just to do the chest compressions and not breathe in your mouth anymore? Okay, that's what this scenario is about. So, however, some researchers believe that chest compressions alone would be more effective than doing both, okay? In the 1990s, a study was conducted in Seattle in which 518 cases were randomly assigned to treatments, 278 to CC plus MMR, and then 240 to CC alone. A total of 64 patients survived the heart attack. That's really sad. 29 in the group that got both, and then 35 in the group that got CC alone. A test of significance was conducted on the following hypotheses. Don't write your hypotheses as sentences, even though they're doing it as an example. That bothers me. We don't do it that way. We only do sentences for chi-squared. Do y'all agree? Okay.
I have a question.
Why?
If I do write sentences, is that going to lower my...
It could take you from a 2.5 becoming a 2 instead of a 3. Don't do it. This test resulted in a p-value of 0.0761. They want us to interpret this p-value. Do you remember that the p-value is the probability of being as high or higher than? Do you remember all that? You might want to write that sentence down. Yeah, this is a sentence we want to know. The p-value of 0.0761, that is the probability of observing a difference between the two sample proportions as large or larger than, because it says higher in the alternative, as large or larger than the one observed, if the survival rates for the two treatments are the same. Yes, you need to know how to interpret the p-value. It could be a multiple choice question or it could be an FRQ question, apparently.
As larger than
The one observed.
Okay, yeah.
Based on this p-value and study design, what conclusion should be drawn in the context of this study? Use a significance level of 0.05. So our p-value is 0.0761. That's greater than alpha, so we fail to reject. Are we all good on reject or fail to reject?
Absolutely.
Less than we reject, greater than we fail to reject. Okay. So, and then you have to write it in the context of the problem. So there's not sufficient evidence to conclude that the treatment that uses the CC alone produces a higher survival rate. So what type of error could we have made?
Type 2.
Only type 2. You have to tie type 1 to reject and type 2 to fail to reject. Let me see if I can remember this. A student on Reddit, thank you Reddit, they suggested that you do art, let me see if I can remember it, and BFF. Okay? Art is type 1. I'll explain it. BFF is type 2. Okay? A for alpha, B for beta, trying to remember the probability of it. R for reject. T when, thank you. T when the HO is true. F for fail to reject. And y'all know this is all HO, even though I'm not writing HO, right? And then F for because the HO was false. I don't know if that helps, but I thought it was kind of cute. Okay. A for alpha, B for beta, R for rejects when, and then T for true. And then type 2 is beta for the probability of a type 2 error. And then fail to reject HO when HO is false. So ART for type 1, BFF for type 2. How do you increase the power? Increase the sample size, increase the significance level as well, the alpha. Okay? And didn't we learn that if you increase the power that you decrease the probability of a type 2? Because one is beta and one minus beta, they go together, right?
Oh, yeah.
This is, yeah, that's okay. So if you fail to reject, the only type of error you could have made was a type 2. Everybody good with that? And then you would tell the consequence of doing that. If we failed to reject, and we shouldn't have in this problem, we failed to reject, so we said the survival rate for the two treatments are equal. But if that's an error, then in reality, wouldn't chest compressions alone be better?
Yep.
So the consequence is that we continue with the standard method and more people are dying when we potentially could save more people if we would just go to chest compressions alone.
That's kind of unlucky.
Yes, ma'am.
Can we go back and quick, how do we know it's as large again instead of as small or smaller?
Because the HA says higher. If it would have said lower, then you would say as low or lower than. If it was not equal to, you would just say it's different from. Okay? This is the two proportion z-test, but I really kind of rather go over the chi-squared with you. Is that okay?
Go ahead.
You can read this one, right? It's just state, plan, do, conclude. You know you can do stat test. Two proportion z-test is number 6. Okay? Don't do it the way I worked it out. Don't do it that way. So my data is that 37 out of 754 people survived. Sorry. 37 out of 754 people survived on one, I think it's on the cardio pump. And then 15 out of 746 survived from CPR. And we're trying to see if cardio pump is greater than CPR. That's my P1 and P2. So that one is greater than. And when I calculate that, you're going to get these same z-score and p-values. So you really don't have to show all that work I showed. You with me? Okay. Let's talk chi-square goodness of fit. Last one we're going to look at. Here we go. Okay, 7 minutes. Give it to me. Ready? 7 minutes, please. You got a spinner. You can get skunk. You can get 100. You can get 200. You can get 300. The way this game works is you keep spinning as long as you want, and we add up what you land on. You stop and walk away with your money, but if you hit skunk before you walk away, then you go back to 0 no matter what you won previously. Does that make sense? Yeah. Okay. So what is the probability that the result will be a number on all of the first 3 spins of the wheel? So if you spin it 3 times, the probability of getting a number would be the first spin, 3 out of 4. The second spin, 3 out of 4. The third spin, 3 out of 4. Agree?
Yes.
You want it to happen on all 3. So that is and. And means multiply or means add. Y'all with me? So I need to multiply 3/4 times 3/4 times 3/4 so you can raise it to the 3rd power and you have your answer. Any questions? Part B. Suppose a contestant has earned $800 on his or her first 3 spins. So they already won $800. So they're like, okay, it's my 4th spin. Do I go for it or do I walk away with the $800? Do you get me? That's what they're deciding. They choose to spin the wheel again. What's the expected value of his or her total winnings for the 4th spin, for 4 spins? So they already have $800. So they could land on skunk and now they have $0 1/4 of the time. Do you get me there? Okay. If I land on $100, then haven't I now won $900 1/4 of the time? I could land on $200, which means 800 plus 200. I would now have $1,000 in winnings 1/4 of the time. Or I could land on 500, so now my winnings are 1,300 1/4 of the time. Does my data make sense? And all you do is you multiply the amount you can win times the probability of each one and add them together. That's how you do expected value. So that's what I did here. I got $800. So at that point, they kind of should just walk away, right? Because they have their potential winning anyway. Now we get to the chi-square goodness of fit test. A contestant who lost at this game alleges that the wheel is not fair. In order to check on the fairness of the wheel, the data in the table below were collected for 100 spins of this wheel. What are our expected values if you spin it 100 times and the wheel is perfect and it's fair? 25, 25, 25, 25. Do you get that? So you would go in and you would put these values in list 1, and those are called our observed values. I know I do this different every time, right? No, clear it for me. What's going on? Clear list 1. Okay, stat, edit. I shouldn't have done that because I need to clear list 2 still. Anyway, observed is 33, 21, 20, and 26. Expected is 25, 25, 25, 25. Y'all understand my data entry there? Are we good there? I don't care about list 3. I'm not even going to use it. For a chi-square goodness of fit test, you go stat over to test GOF. That's D. Everybody see it? Okay. What are our degrees of freedom? You do have to know it for this one.
3.
Okay. Why is it 3? Categories minus 1. It is not 99. Students want to say it's sample size minus 1. For chi-squared, it's always categories. Categories minus 1. So it's 3. Go down to calculate, and you'll see my chi-squared 4.24, my p 0.2367. You do need to put the degrees of freedom. They're going to grade for that. You feel better? Did this help?
All the situations in which we use degrees of freedom that way.
Linear regression, sample size minus 2.
Everything else.
Means, sample size minus 1. Help me, guys. Chi-square goodness of fit is categories minus 1. Regular chi-squared is going to be a matrix, so it's columns minus 1 times rows minus 1. Did we get them all? What else? I can't sit for your test for you. I'm sorry, I would if I could. I wouldn't get a perfect score, but I bet I'd get a 5.